Scientific perspective, then, what's the picture?
In this molecular dynamics calculation, each pair of atoms is programmed to interact with a realistic interatomic force.
So then what really happens when a warm body is brought into contact with a cold one? Thermal energy spreads from warm to cold until both bodies reach the same temperature. This is the state of thermal equilibrium. At first glance, thermal equilibrium seems everywhere. Nature seems impelled toward the state of equilibrium. Hot bodies and cold ones striving toward the same temperature. And falling bodies turning perfectly good work into useless heat. From the physicist's point of view, when nature tends to behave in such a universal fashion, there must be a scientific explanation. And there is. The explanation began as an idea, of course, an idea for the construction of a better steam engine.
There was a young man named Carnot, whose logic was able to show, for a work source proficient, there's none so efficient
as nature would permit, and the logic to come pretty close.
Given a difference in temperature, a high temperature, T sub I, and a low temperature, T sub O, Carnot designed.
In Carnot's ideal engine, the ratio of the heat taken in to the heat wasted was the same as the ratio of the two absolute temperatures needed to drive the engine. In other words, and this was the ideal that stemmed from Carnot's imagination, something that goes in is the same when it comes out. If it's not the heat, and if it's not the temperature, what is it? It's the heat divided by the temperature at which it flows. And according to Clausius, that's entropy. In a Carnot engine, some entropy flows in at high temperature, does its job, and the same amount of entropy flows out at low temperature. So an ideal engine not only conserves energy, the ice doesn't warm up while there's any solid left. Why?
A flow of heat causes the transformation of ice into water at a constant temperature. Therefore, in changing from ice, the water's entropy is increased.
And so, water is a state of higher entropy than ice. In fact, any solid is a state of lower entropy than the same matter in liquid form. Liquid is a more disordered, chaotic state of matter than solid is, and it has a higher entropy. On land, divided by the temperature. Remember, nature always wants to increase entropy. In this case, the entropy of the ice, plus the rest of the universe. If the temperature is very small, it's very bad indeed. Melting the ice would cause a big decrease in entropy of the entire universe. If the temperature is big, it's not so bad. The combined entropy increases when ice melts. That's why, in the grand scheme of...
If you had a movie of that, you'd be able to tell instantly whether it was running forwards or backwards. Because when it's running forwards, the bounces of the ball get smaller each time it bounces. If you saw the bounces getting bigger and bigger, you would know immediately that the film was running backwards. Now what's happening in that case is that the energy of the ball is turning into heat, and that increases the entropy of the universe.